Hello Math 2413 students, here's lesson 9, derivatives and graphs. In lesson 9, we're going to study the effect of derivatives to the graphs. More precisely speaking, the contributions of signs of derivatives, the signs of positive and second derivatives to the graphs. How about third derivatives or higher? Well, we don't consider those in Calculus 1. In Calculus 2, toward the very end in Taylor series, Taylor polynomials, there we consider higher level derivatives, but not here, not yet. Okay, let's begin. First, intervals of increase and decrease versus the derivatives. In summary, if the derivative is positive, then the original function increases. If the derivative is negative, then the original function decreases, it goes down. And then this a comma b notation is the x interval, when x is greater than a and less than b. So when the derivative is positive in that interval, then the original function goes up. It increases in that interval. Look at this picture. Here, a value is 0 and b value is 2. And then in between, please note that derivatives are all positive. Look at these tangent lines, or the segments of those tangent lines. They are all pointed upward. The slope is all positive. By the way, here's an animation associated to that. See this? The derivative remains positive all the way, between 0 and 2. Greater than 0 and less than 2. And then consequently, the tangent line is pointed upward. The slope is positive, so pointed upward. Therefore, the graph is pointed upward. So the function value, y-coordinate, goes up as I move to the right. So the function, the original function, is increasing. Same situation here, except this time is backward. The derivative is negative, and consequently, the original function is decreasing. And here's the animation. Pretty much the same information. Just negative, just decreasing. So in summary, if the derivative is positive, original function is increasing. If the derivative is negative, then the original function is decreasing. Positive, up, negative, down. It's easy to remember. Now, what if the derivative is 0? Or if the derivative does not exist? Such a point is called a critical point. Here are some examples of critical points, but this list is no way close to being exhaustive. But I do have most typical cases, most important cases rather. Local minimum, local maximum, neither maximum nor minimum, but still increasing, but we can consider decreasing version as well. And in this case, yes, it's a local minimum, but no derivative. So here we have horizontal tangent line. That means the tangent line exists, the derivative exists, and the slope is 0. So they fall into this case. Now the fourth case is no derivative case. No tangent line at all, the derivative cannot exist. The left-hand side slope and the right-hand side slope are different, so the derivative does not exist. All these exemplify critical points. And let's go a little bit more deeply into critical points in the next subsection. Now here, I have a little bit more pictures. Still, this list is not exhaustive. Local minimum, local maximum, neither maximum nor minimum, the graph is increasing. Neither maximum nor minimum, the graph is keep on decreasing. And this one is local minimum, yes, but no derivative. And this one here, derivative of 0 for some non-trivial interval. And then, of course, there are other cases too, but I exemplified a little bit more. Local maximum is this kind of situation. It is not the maximum, it is just local maximum, because far away from this, who knows, the graph may come back up and it can go way up. and so on. So it's only a local maximum because this is the highest. compared with only the points around the nearby. And in this case, please note that the sign of derivative changes around this critical point, x equal to c. So less than c, when x is a little bit less than c, the derivative is positive, the graph increases, as you can see from this diagram here. And then from this graph, you can see graph increases. And then hits the maximum here, the critical point here, the derivative is 0, and then derivative becomes negative. And then graph of the original function goes down. Look at this diagram. The derivative changes from positive to negative. Consequently, the original function changes from increasing to decreasing. That's when we have local maximum. Does it make sense? So graph is there, then great. Even if the graph is not there, if you get this diagram, then you can visualize this kind of graph. Similar situation, this time local minimum. Derivative is negative here, so graph goes down, and then hits the critical point at x equal to c. And then that's horizontal tangent, derivative is 0 there. Now derivative is positive, so graph increases. So decrease, hit the minimum, and increase. So that's local minimum. Now look at this diagram. The derivative changes from negative to positive at the threshold of x equal to c. And the graph comes down and hits the minimum and comes back up. Look at the graph and the diagram. They go hand in hand. So if you see the graph, then you can easily visualize a diagram. With some practice, you can easily do that. Now, going backward, get the diagram, and then can you reproduce that graph? That's what you have to do. How to get the diagram is a little bit different story, and we're going to talk about it in a separate video. How about some other case? Okay, here we have a critical point, yes, but neither maximum nor minimum. Graph goes up, hits a critical point, but keeps increasing. Here, graph decreases, hits a critical point, but keeps on decreasing. In this case, neither maximum nor minimum. And put those two together, by the way, maximum or minimum, we use the term extremum, so no extremum. If you don't like this term extremum, then neither maximum nor minimum, that'll do. Look at the diagrams here. Derivative is positive, and then hits momentarily derivative equal to 0 here, and then positive again. So the original function increases, pause momentarily maybe, but keeps on increasing, just like this. Same thing goes on here. Look at the picture and the diagram. Compare those. Let me increase the font so that you can see those better. You see? Positive, up, up, pause, up. Negative, down, down, pause, down. And then, of course, all these exemplify the case where the derivatives exist. And in some cases, they do not exist like this. And then you can have discontinuity and all kind of things. Another thing that I didn't really talk about in detail yet is this kind of situation, the last one. Let me expand the size a little bit. And graph increases and then the derivative is 0. So stay constant for a while for a non-trivial interval and then comes back up. Here, in this interval, the function values stay the same. So the function stays constant for a period of time, for some interval. In this case, every point here in this interval is a critical point. In this case, none of them is maximum nor minimum. If this portion of the graph came down, for example, then all these points would have been local maximum. And vice versa. If this portion left-hand side had been upward here, come down, they hit constant and go back up, then all points here would have been local minimum. But these are rather singular cases. The majority of the time, we're going to have to deal with these cases. A single isolated critical point, local maximum, a single isolated critical point, which is local minimum. I said backward, minimum, maximum, and then single isolated critical point here and there, but neither maximum nor minimum. We call those kind of points inflection points, but that's something we're going to discuss in a little bit more detail in a separate video. In this kind of case, we have either local maximum or local minimum or neither or whatever, discontinuity, whatever. The derivative does not exist. And then for a constant for a while, let's see. I guess we did cover all the variants, I guess, even though the pictures are not exhaustive. There are other kind of pictures, but we did consider all those cases, I guess. Finally, one final comment. I'm going to use the term critical point, but point literally means a point. So we have to have x coordinate and y coordinate. X comma y is c comma f of c, and c is the x value, so y value should be, of course, the function value f of c. But most of the time, people do not care about the y coordinate. There's a reason I didn't draw this picture with coordinate axis, because nobody really cares about the y coordinate most of the time. If that becomes necessary, you can always plug in x equal to c and calculate. C, this is important. So critical point at x equal to c, the x coordinate is something I'm going to emphasize. The x coordinate of the critical point, not the y coordinate. Y coordinate is not very important. Now some people separate those into the critical number, x coordinate, and critical value, y coordinate. So critical number is x coordinate, critical value is y coordinate. Put those together, then we have a critical point. That's the way our textbook author explains, but in my opinion, that's a bit too many terminologies. So I'll try not to use these, critical number, critical value, those kind of things. Majority of the time, I'll just go ahead with critical point, and then I'm going to specify the x coordinate of the critical point, or the function attains a critical point at x equal to c. Okay, so much for the intervals of increase and decrease and critical points. We're going to talk about the concavity in a separate video. For now, we are done with the first half of section 1.